All right, now I want to get to your specific advantage as a quantum informationalist. Is it okay? Well, actually, let me spell out the way that I see it from the outside. It seems like if you love general relativity, if you're a relativist, the approach that most resonates with you is loop quantum gravity. And then if you're a quantum field theorist, the approach that most resonates with you is string theory. It's like seen as an extension of quantum field theory. And those are the large two broad ones. But then there's quantum information. So if you go into quantum gravity, sorry for saying the word quantum gravity, but you understand the reconciliation of quantum mechanics and gravity.
Right.
From a quantum information perspective, you generate different ideas, much like you do if you're a relativist versus quantum field theorist. So there's Chiara Marletto, who also came to constructor theory from being in quantum computing / quantum information.
Right.
And you have a different approach. So can you talk about the advantages that someone who's trained in quantum information has when attempting to make coherent quantum mechanics and gravity?
Right. I mean, it's a good question, and I'm not sure how much of it is related to the community of quantum information theory versus the actual study of quantum information theory. But I would say that in terms of having a deep understanding of quantum theory, that is, I think the quantum information theory community and the quantum computation theory community really has a very deep understanding of quantum mechanics. So one of the reasons I got interested in quantum information theory is because I felt I needed to understand quantum theory better. If you come, in the high energy physics community or the gravity community, I think there wasn't an appreciation for what parts of quantum theory you could modify and what parts of quantum theory you would have a lot of trouble and get into trouble if you modified. And I'm not exactly sure why that's the case. It didn't have to be the case, but just from a community point of view, that is the case. And maybe it's because if you are studying, say, computation, you're interested in classical computation and quantum computation, and you can start thinking about other forms of computation from other, how could you modify our physical laws and how would that change the laws of computation? And so for whatever reason, I think there's a deep understanding of, how you can change quantum theory and how you shouldn't change quantum theory. A good example of that is linearity. If you come from quantum information theory, there are certain parts of quantum theory which we wouldn't change. We would want our theory to be linear, meaning that if you flip coins and prepare different sorts of systems, depending on the outcome of the coin toss, then your dynamics shouldn't be sensitive to what the values of those coins are. Or, for example, we would say that any theory of nature, if it's a theory that acts on the density matrix of a quantum system, it should make sure that probabilities get mapped to probabilities, and then it has certain mathematical properties. So I think the quantum information theory community is just quite used to considering different sorts of dynamics and what sort of dynamics is allowed. And maybe that comes a little bit because we study things like decoherence and we study, quantum systems which interact with other quantum systems like an environment which we ignore and forget about. And so the dynamics is, in some sense, a bit more general than what is considered in straight up quantum theory that you might learn in an undergraduate quantum mechanics course.
What's the name of the approach? Does it have a name?
So it I guess has gone by, it has many names in some sense. So I called it a post-quantum theory of classical gravity because gravity is classical, but quantum mechanics is modified slightly. It doesn't need the measurement postulate, so it's like a post-quantum theory. It had been, people have proposed for probably almost as long as there's been an idea that we should quantize gravity. There's also been people who have suggested that maybe gravity could be classical, and so there's something that goes by the name of hybrid gravity or classical quantum gravity that has also existed out there. Yeah.
Okay. You don't call it by a moniker. You just write papers about it. But when you're referring to it, you don't call it, this is classical quantum gravity or this is post. Because calling it post-quantum is a description. It's not like a title like geometric unity or causal dynamic
Right.
triangulation.
Right.
I want you to explain what MG is, but do so with the transition of why you don't like the current approaches to making gravity and quantum mechanics cooperate.
Well, let's start with that. I wouldn't say I don't like the current approaches. I think I'm more of the view that there's been this assumption, and I think based on some incorrect arguments, there's been this assumption that we have to quantize gravity. And we started off by starting with the Einstein equation, where you have matter on one side, which is quantum, and it should be equal to something which is classical, and that doesn't make sense. So people have thought we have to quantize gravity. And there's been a bit of a discussion about that, I think in part because we've spent more than 100 years of failing to quantize gravity. And so because there's been about this 100 years of failure, one can, it's useful to think, well, is this really the right approach, or is it possible that we've gone down and are taking a wrong direction? So I don't know what the correct answer is. I don't know if gravity is quantum or classical or something else. I suppose my perspective is just that we should, because the arguments that people marshaled claiming that we had to quantize gravity, because those have turned out to be incorrect, I think it's important to revisit the issue and to explore the possibility that maybe gravity could somehow be fundamentally classical. And I think there's some motivation for that. I don't think it is just a random idea that, okay, maybe gravity is special and classical. I think there's some, good arguments you can make in favor of not quantizing gravity. So that's my perspective, just that it's possible that it could be classical gravity, and there's some reason to believe that gravity is special and different to the other forces and therefore should remain classical.
What would some of those reasons be?
So I think that, gravity is different from other forces in that it is, what Einstein's general relativity tells us is that matter causes space-time to bend, and it's that curvature of space-time that is the manifestation of gravity. So, we're just following a straight line. We're just, free falling in a geodesic, and that's because space-time is curved. That gives us the appearance of a force, which we call gravity. But it's the only force which can be described universally as a geometry. So, in that way, gravity is special. It universally describes this background causal structure, which the rest of, which all the other fields, live in this arena of this curved background geometry. And so there's, there are reasons to imagine that background structure has to be fundamentally classical. And I think one of the main reasons I would give for that is that the causal structure seems to be, which gravity gives us, so it gives us this causal structure. I don't think that we really know how to do quantum theory without that causal structure. At least I don't know any way of doing it. And we can try and quantize it, but then in some sense, I feel like we lose our legs. We lose all this background structure, which we needed in order to perform quantum theory.
And is this related to, you make a non-canonical choice at some point?
Right.
And so you lose something that's special about general relativity.
That's right. So, you can imagine, let's just even start with how physicists, like what is physics? So, usually what we do is we specify some system at some initial time, and then we ask, how does it evolve, and predict what's going to happen to it at some future time. And in a quantum theory of gravity, just merely those statements are difficult to really make precise. So, for example, if we want to specify the initial state of the system, well, in a curved space-time, that's not so easy, because you have to find some hypersurface across all of space, and you label that and say this represents an initial time slice. That choice is not there's a number of ways that you can slice up space-time into some family of hypersurfaces, these spatial Cauchy surfaces that are kind of evolving in time like this. And you can do that in quantum field theory because you have a definite causal structure. So if I want to say that this curved slice here represents the state of the system at time t equals 0, then that's a well-defined statement. But I don't know how to make that statement if the geometry itself is the thing I'm quantizing, because then I don't have that, causal structure. Now I can imagine just choosing one, and I just choose some particular slice, and I then just quantize it as I would any other field theory. But as far as we can, as best we understand, the quantum theory of gravity that we would come up with will be dependent on this choice of how we chose to slice up our space-time.
What if the loop quantum theorist would say, hey, the constraints on such a system in our theory are such that it's independent of this, even though we chose a Cauchy surface. The observables are independent of such foliations. So does that not get over the objection?
Well, so I guess the problem with, there's two approaches you could do. One is you can just hope that your theory will be independent of the choices. You can try and have a completely background independent approach, which is what loop quantum gravity tries to do. And in particular, what the spin foam, they use something called spin foam networks, which is the object of interest, and take a background independent approach. And the problem then they face is that they have no idea how to recover the classical geometry at the end. So, there's no way for them to know, or they haven't at least been able to show that in some low energy limit, they will recover gravity, classical gravity.
Right.
Or, on the other hand, in string theory, they kind of take the other approach where they have a background dependent theory and, hope that, they'll be able to either show that it's independent of that choice or come up with a background independent approach. And some would say that, a lot of string theory now is something called ADS-CFT or holography. And there's some claim that is to some extent or to a larger extent background independent.
So this post-quantum theory of yours, can you please describe it?
So the main idea is that you somehow take seriously the idea that maybe we need this classical background structure of space-time, and then it has to be classical. And so you just start with, you can start simply by saying, can we consistently couple classical systems and quantum systems? Is there any way to do that? And at the moment, we have only two frameworks for physics. We have quantum theory and classical mechanics. We don't really have, at the moment, any kind of credible other frameworks which are beyond quantum theory, for example. And so the first question you can just ask is it possible to consistently couple a quantum system with a classical system? And there's been a huge number of kind of approaches to that, where people have tried to consistently couple a quantum system with a classical system. And almost all of those have been unsuccessful. But actually in the the mid-90s, there was actually a few examples of such consistent coupling due to Dioschi and due to two people named Blanchard and Jacek. And they found some examples where you can consistently couple a quantum system with a classical system. And so the first thing we had to do was just to say, okay, what is the most general form of dynamics that we can come up with, which couples a classical system with a quantum system? So that's the first thing you do, is you derive the most general dynamics that can do that.